Welcome to an ultra-scale quick take video featuring Xilinx's DMA subsystem for PCI Express. Starting with Vivado 2016.1, Xilinx will be making available a full-featured DMA specifically built to work with PCI Express. In the video today, we'll go over a very quick look at typical PCIe DMA use cases. We'll talk about the features of the DMA subsystem for PCIe. We'll walk through a Vivado implementation, and finally we'll put it in hardware and see how it works. So a typical DMA operation for PCI Express is really all about moving data between the system memory that our host has access to and our PCI Express endpoint. Now, oftentimes what we see are FPGAs are used for data acquisition or possibly acceleration, and what we want to do is move data back and forth between that endpoint and the system memory. So the DMA is available with a large number of devices, starting with the Vertex 7 devices that are capable of Gen 3 PCI Express. It is also available for Kintex and Vertex UltraScale devices, as well as the entire UltraScale Plus family. Now, it works with what we call the PCIe 3.0 block and beyond, and that is what is in all of these devices that are highlighted. Now, the other nice thing about this DMA is that the cost is absolutely right, as it is free to use and is widely available in Vivado 2016.1. When using the DMA, the first choice that needs to be made is which type of interface are you going to use. Are you doing an AXI4 stream interface, which means that you're typically doing RTL design, or are you doing an AXI4 memory map interface, which means that you're doing some kind of AXI subsystem? If you choose the stream interface, you'll have the option to have as many interfaces as you have as the number of channels that you've specified. If you choose the AXI4 memory map interface, you will get one interface regardless of the number of channels. The DMA engine is a scatter-gather block DMA engine. It has up to 4 read and 4 write channels possible, and it has either 64, 128, or 256-bit data bus operation up to 250 megahertz, and that is going to depend upon the link width and speed that you've selected for your PCIe design. Now, in addition to those features that we just mentioned, some additional features are it has 256 megabyte transfer size, it has unlimited descriptor size, so you can have as many descriptors as you would like. It has an option that does contiguous descriptor prefetch. This means that if descriptors sit next to each other in local memory, they will be read with a single read instead of multiple reads for one per descriptor. And finally, it has MSI, MSIX, and INT-X interrupts. Now, there are a couple sideband interfaces that are useful for designers. The first one we're going to look at here is called the AXI4 Lite Master interface. And what this does is it allows single D-word PCIe reads and writes to be sent over the PCIe link, and they will get translated into an AXI memory map. And these are any transactions that hit bar 0. We also have a Control Lite Slave interface. So again, this is an AXI4 memory map interface. It's a light interface, so it supports single D-word reads and writes to look at control and status registers. And then finally, we have the AXI4 Bypass Master. And this master is for high performance applications where maybe the FPGA in this case is the target of a DMA transfer, and we need to be able to accept really high performance reads and writes, and that is mapped to bar 2. So without further ado, let's go ahead and get started and show you how to make this in Vivado 2016.1. So the first thing we need to do is create a new project. Go ahead and give it a name that you would like to have, and go ahead and advance forward until you get to the part selection location. Here, select the Boards tab, and this will give us easy access to the KCU 105. Now, while this is generating, what we could do, one of the things that we could do is we could go ahead and generate a IP core from the IP catalog for the DMA engine, and then right-click on that XCI file that gets generated, and then say Create Example Design. Instead, I'm going to show you another way to do it, which is just to create a block diagram to show you really how easy it is to get up and running. So go ahead and create that block diagram, give it any name you want, and then select the Boards tab. Here we're going to select the dip switches, and the rotary switch is just GPIO that we can access using the AXI Lite master interface that we talked about earlier. Once you do that, select PCI Express. It gives us an option here. We want the DMA. We'll go ahead and select the lane width and make it a by 8, and we'll double check on that in just a minute. But go ahead and generate that design, and once that comes up, what we want to do is go ahead and select DDR4 memory, because what we're going to do in this design is we're going to have the DMA connected to DDR4 memory as well as the GPIO. All right, once we have those in place, we'll go ahead and run block automation. So here we can go ahead and select some different things that are available, different options that are available to us for the DMA engine, sort of a quick access. We'll go ahead and set one channel for both upstream and downstream, or read and write in this case, and let that generate. And then once that's done, we can go ahead and look into it, and we can push in, and we'll see that the different options that we set in that quick menu have indeed been transferred here. So we see we have the AXI Lite bar. It translates to 0. We're not going to use the bypass interface, the high performance interface. And here we see we've got one read and one write channel, just as we specified. So we'll go ahead and cancel out of that. Now let's go ahead and run connection automation. This is going to connect up a lot of our things automatically and really simplifies the process. So once we get that populated here and relayed out, you can see I've got some nice color coding on the clock and reset nets. If you want to know how to do that, you just go to the options here and you can select colors, and then you can change those. So that really helps out in sometimes seeing what's going on in your design. So now we've got, with those few simple steps, we've got our design pretty much complete. Here we'll go ahead and look at the address map, and we see that the DDR memory is mapped to address 8 million hex, and we're going to go ahead and add our GPIO just to address 0, and that will match up because we left our address translation register for that AXI Lite interface to 0. So anything that hits that bar will go to address 0 or whatever offset has been set to. All right, so we will go ahead now. Let's go ahead and save our block diagram. And let's go ahead and validate it. Make sure that it looks okay. Once we've validated it and it looks fine, we get no critical errors, we can go ahead and exit out of here. And that's really all it took to get our hardware design in place. Now we do need to add the top level RTL file to this project, and in this case what we do is we'll go up to our block design, right click on it, and go ahead and create the HDL wrapper. Because we don't want any customizations made to this wrapper, we'll go ahead and let Vivado manage it, and it will wrap our design up into that Verilog file. And now all we have to do is go ahead and generate a bit stream. It's as easy as that. So we go ahead and speed this up so we don't have to wait through the entire process. And now we'll go ahead and open the design just to make sure that timing's been met and everything looks good. So you can see there's actually a couple check timing items here that are highlighted down in the bottom left. If we go and open those up, we can see that there's just no input delays and no output delays on the dip switches, the reset. If we wanted to do some TIGs, or if we cared about timing, we could add constraints and rerun the design. For this case, we'll go ahead and leave them as is. They're not critical. So now I have this design hooked up to a KCU 105, so we'll go ahead and connect to it. And once we're there, we'll go ahead and reprogram it with this new design. All right, now that it's complete, we're to switch over. We're going to switch windows here. Well, actually, before we do that, just to give you an idea, we can look at some of the system monitor dashboards. We can see what the temperature is If we had some chip scope in here, we could bring up those waveforms, but for now we'll leave it as is. And the next thing we'll do is we're going to switch over and take a look at the Linux system that we have running that has the KCU 105 enclosed in it. All right, so here we are on our Linux box, and you can see that I've already pulled up answer record 65444. This is where we keep our DMA driver and software. So now this is an example driver. It comes with some documentation. There's a zip file that you can download. What we're expecting is customers to be able to take this driver and integrate it into their complete driver and application as they choose. All right, so I've downloaded the zip file. I'm going to go ahead and make a directory here called DMA driver. We will copy over that zip file from that directory and unzip it. And once we have it unzipped, we can go ahead and push in there. And at the very top level, we'll see there's a README file there. Now, I'm not going to go through everything, but you can see there's a usage section. We're just going to follow that usage section in this demo and see if we can get our design up and running with data being transferred back and forth between our design and the DDR memory, our application, I guess, in the DDR memory. All right, so we go ahead and push into the driver directory. We type make to compile the driver. We go up one directory to tests. We go here, we go ahead and compile our tests. Now, in this case, the .sh files, the script files, were not set as executable when I unzipped them. So I'm going to go in and just make sure that all of the .sh files are set to executable. We'll go ahead and copy over some of the files required for this driver to operate into the rules.d directory. I've already done it once, but we'll go ahead and just say overwrite them. And then we can go ahead and run the load driver script, and we see that it worked correctly. Now, in the example design, if you remember, we set that offset to 8 million hex of where the DDR memory is. So in the script file, what we see is the run test is actually going to run something called DMA memory map. And what we need to do is we need to change the offset, because right now the offset is set up to go to address 0. And this address offset that we're specifying is actually the AXI address offset. And so what we're going to do is we're going to go ahead and just take the address offset and we're going to add 8 million hex to it, or as it turns out in decimal, it's some sort of funky number that we'll go ahead and get put in here, as you'll see on the screen. And we need to do this in both the write location, where we write the data, as down as where we do what we call a read, or a card to host transfer. All right, so once we have that in place, we can go ahead and run our tests. And we see that our test runs, we're able to transfer data back and forth here between the system memory and the DDR4. So that completes our walkthrough. Remember, the PCI Express DMA IP Subsystem is available in Vivado 2016.1. We hope you'll check it out for your next design.